Hi, everybody, and welcome to our online lecture for the rest of Chapter 5, Section 1 on sequences. So just as a quick recap, in class yesterday, we were able to start Chapter 5, Section 1. So I do have just my notes from before. So we talked about what a sequence is and some key terms there. So actually, what is a term, initial term and final term, or the fact that things could be infinite. We did an example, actually writing out the first few terms of a sequence. So we were able to figure out how to write that sequence by using the formula given. And then also really important to note is your starting value. So here in this first example, K started at 1. So our first subscript was 1, A sub 1. But when we did the sequence for the B group, our starting value was actually 2. So our first subscript was B sub 2 there, and 2 was what we were plugging in to our formula. And that was actually an interesting example where we saw that those two formulas actually produce the same sequence. So there is actually often more than one answer or more than one way to write a sequence. So you may notice that in some examples. And then we ended last class doing, again, one more example of a sequence. So here we did the first 6 terms of the following sequence where we were plugging in for the exponent. Here our starting value was at 0. So our first term was C sub 0. We plugged in 0 wherever we saw J in the formula, and then we simplified. This time we wanted 6 terms. So make sure you count your terms and not just look at the subscripts there. So 6 terms are 0 through 5. And in this example here, we did notice an alternating sequence, meaning that the signs are alternating. So 1 to -1, 1 to -1, and so on. So we're going to pick up here. So we did the first few examples together yesterday, and now I'm going to pick up with our next example. And again, go through quite a lot of examples here in Chapter 5, Section 1. So our next example is example 5.1.3 in your text. It says to find an explicit formula for a sequence with the following initial terms. All right, so our terms are 1, -1/4, 1/9, -1/16, 1/25, and -1/36. So here we're going the opposite direction. Instead of me giving you the formula and finding the terms, you're going to go the other way. So you're going to have a set of terms and try to work backwards to the formula. These are definitely trickier. So they do take some trial and error. So it's a good idea to kind of guess what you think the formula may be. Actually try out the first few terms and make sure it works. Or if it doesn't work, see how you can tweak it. You also want to look for patterns. So one thing I'm going to notice is I do see the alternating sign like we saw in our last example. So this idea of having that -1 to a power come in is probably going to have to come in place somewhere here so that I can change that sign back and forth. The other thing, hopefully that you're noticing, it may not be obvious in the beginning, but it is if you kind of keep looking, is that our denominators are actually squares. So if you pay attention here, this is actually the same as -1/2 squared, and this is +1/3 squared, -1/4 squared, +1/5 squared, and -1/6 squared. So you can see the pattern actually is just the numbers going up by 1 and being squared. Now the pattern actually does hold for the first case because you can always divide by 1. So, this is 1/1 squared. This is the same answer, right? 1/1 squared is just 1. So I actually do have a very clear pattern here on what's happening. So now I have to actually guess at what I think the formula is going to be, and then I'm going to check it to see if I guess right. And if I did not, I'm going to go back and fix it. So this is a great one to actually try on your own. So if you're at home and you want to give it a try and kind of think through some options, you can pause right here. A good one to start by trying is doing, again, something with that -1. and something with the squares, right? So think about what's happening. I have that sign change going back and forth. So I have to bring in like a -1 to a power somewhere to get that changing sign. And then I can see my denominator is about being squared. Now I'm going to start with 1 here because my denominator is a 1. So that kind of makes sense, like 1 squared and then 2 squared and so on. So let's try it and let's see if it actually works. Got a couple different colors here. So let's check it. And you actually check it by trying to find the first few values. So here I'm going to start with 1. So I'm going to do a sub 1. So I get -1 to the first power over 1 squared. -1 to the first power is -1. 1 squared is 1, so this is -1. If I do a sub 2, I have -1 squared over 2 squared. -1 squared is +1, and 2 squared is 4. And if I do a sub 3, I get -1 to the third power over 3 squared. That would be -1 over 9. So I'm going to just pause for a second, and I'm going to notice that I'm really close, but I'm off, right? So I can see I have the 1, the 1/4, the 1/9. So that's looking good, but my signs are not what they should be. They're backwards. So I'm going to have to do a little bit of tweaking. And you can actually tweak this a couple different ways. So there's, again, more than one way to do it. The way that I ended up tweaking it as my main idea is I said, well, I want to switch these signs. So I would like this one to be a positive, which means I need an even exponent there. So one way to do that is instead to make this k plus 1, because then this would turn into a 2, which would make it a 1. This would turn into a 3, which would make it a -1, and so on. So again, there's more than one way to do this, but if I switch and try this new version, then what I end up with is a sub 1 would be -1 to the 1 plus 1 over 1 squared, which is -1 to the second power over 1 squared. So that gives me the 1 over 1 equals 1 that I'm looking for. If I try a sub 2, I would have 2 plus 1 over 2 squared. So that gives me -1 to the third power over 4. So that's going to keep my 1 negative, which is what I need. And let's check one more. So I'd have 3 plus 1 for my power over 3 squared. So -1 to the fourth power over 9 gives me that positive, 1/9 that I'm looking for. So that change looks great. So what my final formula is going to be then is going to be a sub k is equal to -1 to the k plus 1 all over k squared. And again, I'm going to have integers k greater than or equal to 1. Now, again, there's more than one answer. So other ones that also work as a side note, instead of adding 1 to the numerator, I could have subtracted 1. That would also sort of change my power from odd to even and swap them. So for integers, k at least 1. So you can check this at home. And a third option that could have worked is I could have left the -1 to the k the same, but I could have changed my denominator instead to k plus 1. And I would start it at 0 in this case. So if I plugged in 0 here, I'd get the +1. And then if I plug in 0, I'd get 1 squared. So that would also work out. And I'll let you try these two at home and check the first few terms to see that they do work. So more than one answer here. And there's probably more as well. These are like the 3 main ones that I thought of. But again, pick something that you think may work, test it. Don't just assume it works. And then if it doesn't work, you can go in and tweak it. And of course, there's often more than one way to do that. So for our sequences, you want to make sure you can go in both directions. So you can have a formula and find the terms, or you can have the terms and work backwards and find that formula. And it definitely is trial and error. So it's not, that way it's not as straightforward. It does take a little bit of practice. And always making sure to check your results. All right, let me grab another color. All right, so we're still in the same section, but there's a lot of topics in this first section. So the next big thing we need to talk about is called summation notation. All right, so we're going to let m and n be integers such that m is less than or equal to n. And summation notation looks like this. So this is the symbol that we use. All right, so as I was saying, here is the summation notation, what it looks like. So you have this symbol here, which means to sum. You have a upper limit and your starting value, and then you would have some sort of formula for the group, we'll say, or for the equation here. So a couple things to note. So this value up top would be your upper limit. This value m would be your lower limit, so your starting point. K we call the index. And what this looks like is this. So if, m is our first value, our first piece here, again, because I don't have the actual formula, would be a sub m. And then this symbol means to sum. And remember, sum means addition. So what you're doing here is you're basically adding up the sequence terms instead. So it would be am, and then plus the next term. We'll say m plus 1, plus the next term, m plus 2, and we go all the way until we reach the subscript of n, a sub n. And that is what this looks like. So a couple of things here. This symbol is actually a Greek letter, capital S. It's called sigma. And it does mean to sum or to add. It's a pretty common symbol in mathematics, not just in discrete math, but it occurs in a lot of calculus lectures. We use it in statistics as well. So if you see that capital Greek S, that's sigma, again, it's probably going to mean to add. This is a pretty universal notation in most math classes and other fields as well. So we're going to be adding here. All right, let's look at an example so you can actually see something concrete and what this would look like. So let's let A1 equal -2, A2 equal -1, A3 equal 0, A sub 4 equal 1, and A sub 5 equal 2. So we're going to just do some beginning ones here where you have the terms already kind of pre-done for you. And we're going to compute the following. So the first summation is going to go from 1 to 5 of A sub k. So here, instead of having like a formula or anything, they're just going to give you the values already ahead of time. And we're going to add from A1 all the way up to A sub 5. So what this looks like here, A sub 1 is -2, A sub 2 is -1, and so on. So I'm basically just going to add up these values here. And if you add them, you do get 0. And that's your answer. That's it. So we're going to use the same terms again, but this time your summation is going to go from 2 to 2. So what happens here, you're starting at A sub 2 and you're ending at A sub 2. So you're not actually adding any other terms here. This is what one single term would look like using summation notation. So the answer for A sub 2 is -1. And of course, you could go and just do some of them. So let's do K is 1 to 2. So here you're adding A sub 1 with A sub 2. So -2 plus -1 is -3. Let's look at another example. So this time I'm going to do a more formula-based one. So this is example 5.1.5 in your text. And we're going to compute the sum from 1 to 5 of k squared. So here they're not giving us our terms ahead of time. They're giving us the formula instead. And this is a 5, by the way. It looks a little bit like a 6. That's a 5. So we're going to go from 1 to 5. So I start by plugging in 1 first. So I would have 1 squared. And then I'm going to plug in 2. So 2 squared. And then I'm going to plug in 3, 4. And the last one I'll plug in is 5. So that is where I'm going to stop. Each time I use the formula, and because it has the sum symbol here, you're adding in between. So I would have 1, let's see what, 4, 9, 16, and 25. And if you take out your calculator, you should get 55 there. So sometimes you may have the terms pre-written out. Other times, more likely than not, you probably have a formula that you'll be using to plug into. All right. This section is a nice change of pace. A lot of examples, kind of going back to more of, I guess, traditional math, what we're kind of used to. Next example is 5.1.6. Right? So sigma is going here from 0 to n. We're going to use I for our index this time, in expanded form. So what this would look like as expanded form is basically we would write out the terms. So instead of having it with a summation notation, you're actually going to write out with the plus signs in between. So I'm going to start with 0. So this would be -1 to the 0 power over 0 plus 1 plus, then I do the 1, -1 to the 1 power over 1 plus 1. Then I do the 2, -1 to the 2 power over 2 plus 1. Then I do 3, -1 to the 3 power over 3 plus 1, and so on. So you're going to keep going. Now here, I don't have a specific ending. I'm ending at n. So what you can do once there's a clear pattern, I would definitely do it at least a few terms. I would do a plus sign with a dot, 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 and then another plus sign. And that shows that there's others in between. And then our last one is going to be to the nth power. So -1 to the n over n plus 1. And then I am going to clean that up a little bit. So here, -1 to the 0 power is 1. So this is 1 over 1. Here I would have -1 over 2, +1 over 3, -1 over 4. And finally, I'm just going to clean up this 1 over 1. So 1, what you could do too is you could clean up the subtraction. So plus and negative is the same as minus. So that's pretty common as well, is to switch those adding and negatives to subtraction there. And that would be our final answer in expanded form. So actually writing out what the addition would look like, and again, showing enough so that you can see enough of a clear pattern there is what you really want to do. And of course, we can go the other way as well. So our next example, this is 5.1.7. Says to express the following using summation notation. All right, so here they're going to give us the expanded form, and we have to work backwards and put it back into summation notation. So 1 over n plus 2 over n plus 1 plus 3 over n plus 2 plus n plus 1 all over 2n. And again, these are definitely trickier. It's much easier to have the formula and go to the terms or, the individual pieces rather than to go backwards. So there is a bit of trial and error that has to happen here. So if you kind of think about what's going on, it is a little tough to see. There's different ways you can do it, but the one that I came up with is, I'm going to use I here for my index, is I plus 1 over n plus I. And I'm going to actually start at I is 0 and go all the way to n. So what I'm noticing here is that my numerator is 1 bigger than what I'm adding in the denominator. So that's why I have the I plus 1 and then the I here. So that, I think, is a good guess. So the n is consistent every single time. That's not changing. So I'm leaving the n as it is. And then the thing that's changing is the number on the top and the bottom there, right? So the number on the top is increasing by 1, so is the number on the bottom, but the number on top is like 1 unit ahead. So if I do a plus 1 there, I think it's going to work. So let's actually check it. Make sure it actually does work. So if I start with I equals 0, for instance, and you can just write out the sum or check it how you want to, but if I plug in 0, I would have 0 plus 1 over n plus 0, which would be 1 over n. So that seems to work for the first one. If I try I as 1, I get 1 plus 1 over n plus 1, which is 2 over n plus 1. So that seems to work. If I try I as 2, I have, let's see, 2 plus 1 over n plus 2. So I have 3 over n plus 2. That seems to work. Now, do check the last one, though. So let's make sure it actually works for n. So I'd have n plus 1 over n plus n. And n plus n is actually 2n. So it actually does work. So this would be the correct summation notation here that we would use. But again, they do take some trial and error and watching for patterns. So the things that I noticed is, 1, the n remained in all of the cases. So that stayed fixed. And then I noticed that the numerator was always 1 bigger than what I was adding in the denominator. So that's why that plus 1 came in here. Again, there's different ways to do it too. So this is just one possible answer that you could have gotten. All right, let's try another example. So this is example 8 in your text. It says, what is the value of 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 to the n when n is equal to 0, n equals 1, and n equals 2. So they're giving you a general pattern here. It doesn't ask you to find the summation notation, but if you wanted to practice, we can definitely see that we have a 2 to a power idea going on. So that's kind of what the formula you'd want to try to work out or tweak a little bit, is some sort of, 2 to the I power. And the one that works here is if you start your indexing at 0 and then you end your indexing at n. So again, it's not really required here to do that, but if you find it helpful or if you just want to practice, that would be the summation notation. All right, now these are 3 different problems. The first one is n is equal to 0. So when n is equal to 0, you are stopping at the power of 0. That is it. So you're going to do 2 to the 0, which is just 1. For B, you're stopping at n is 1. So notice here, if you look at the formula, you start at 0, but now we're going to stop at 1. So you're still starting at 0, but you're only going to 1 now. So you do 2 to the 0 plus 2 to the 1. So that becomes 1 plus 2, which is 3. And then when n is equal to 2, I would do 2 to the 0 plus 2 to the 1, and then I'm going to stop at 2 to the 2. Right, to the second power. So I only go as high as the n says. Just because there's lots of different dots here does not mean there has to be like infinitely many terms. It's just whatever we decide our maximum is going to be. So here I have 1 plus 2 plus 4, which is 7. And it didn't ask here, but again, you could really pick any n. I could do n to the 5, in which case I would add 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2, 4, and then I would stop at 2 to the 5th. And I'll skip this, but you can just use your calculator and find the answer there. Okay, so for something like this, don't let the formula throw you off that you have to use everything there. That's a big mistake students make. If your n is only to the 0 power, then you stop at the 0 power, right? So you have to look at that pattern where you see that the exponent is to the nth power. We start at the 0 power, but then you stop where it tells you to stop. So you only go as far as you need to. Okay. A more precise definition of summation is a recursive definition. We'll do more of this later too. And it looks like this. If m is any integer, then the summation from m to m of a sub k is just a sub m, right? Because you're just plugging in m there. That's your starting and your ending value. And the summation from k equals m to n of a sub k could also be written as k equals m to n minus 1 a sub k plus a sub n. And this is true for every integer n greater than m. So what's really happening here, what kind of the goal of this is that you're sort of just separating off the last term. And this is actually a pretty common thing to do with summation notation sometimes, is to either separate off the first term, which is kind of what they were showing here. So if you have just going from one term to one term, you could separate off the first term. And then what you could do is you could start your next summation at m plus 1 to n or something like that. Or what's also common is you could separate off the last term. So what's going on here is you're still going from m to n. It's just that you're going from m to n minus 1, and then you're adding in that singular term here. So this piece is going from n to n of a sub k. So it finishes that last piece of the summation. We'll do a little bit with it here, and we'll do a lot more with it in chapter 5. It's a helpful tool for certain proofs as well, and trying to find patterns. So sometimes it helps to kind of separate off a term or a couple terms in one direction to help us with the patterns or to help us to prove things as well. All right, so this is example 5.1.9. A says to write k going from 0 to n to the 2k plus 1 plus 2n plus 1 as a single summation. So one thing I want you to note here is that these are actually two different things. So this is one group right here, and then you have plus this other piece here. So it's kind of like this example right here, where you're separating off one of the terms. If the summation was for everything, so it's not here, but as a side note, let me grab another. If I wanted the summation to be for everything, for instance, I would write it with parentheses. I don't know, like this. This doesn't really make sense, but if it was something like that with parentheses, then it would be for the whole piece. That would be different. If it doesn't have parentheses, then those are two separate things, okay? So this would be all for the summation, not separate. Okay, so just a little kind of note here. So you do want to be careful about the notation there. So parentheses, everything is for the summation. If there's no parentheses, it's just whatever the summation is next to. So this is one thing, and this is plus another thing. So what you have here, just kind of looking at a few terms, right? you're going from 0 to n. So you'd have like 2 to the 0 plus 1. Oops, hang on, I made a mistake here. Let's get rid of this. We don't need that plus 1 there. So that's kind of a complicated problem. There we go. Get rid of that plus 1. So that makes more sense. 2 to the 0, that's a little bit easier. And then 2 to the 1, 2 to the 2, etc., all the way up to 2 to the n, right? So that's what that first piece is. And then if you notice, the second piece is saying, oh, and then plus 2 to the n plus 1. So if you look at it, you really have the same pattern the whole way. There's really nothing new going on here. You're just going one extra term out. So we're kind of reversing this formula here and bringing it back together. So we could also write this like this. So the sum starting at 0 all the way to n plus 1 to the 2k. Right? So making that little change here, instead of going from n, going to n plus 1 allows us to bring that last term back in for this particular example. And we can do it the other way as well. So let's write the sum from I equals 1 to n plus 1 of 1 over I squared by separating off the final term. So again, going the other direction. So now let's separate that final term off. So what's happening here is you're going to go all the way from 1 to n, right? Because this goes to n plus 1. So what's one unit down would just be n, right? N plus 1 minus 1 is just n. And then we would add that separate or last term here. So if I plug in n plus 1, it'd be 1 over n plus 1 squared. So this right there would be that n plus 1 term, right? And then here what we did is we stopped at 1 fewer or 1 less than what was already given. So that's how we can also take that final term off. So we go 1 less and then actually plug in for the final term and see what the result would be. Okay. As you're reading and taking notes too, make sure you pause the video as you need to. So if you need some extra time to write the notes out, feel free to pause as many times as you need to or to take breaks. Like I said, this is a longer section, and there's a lot of examples for us to go through. All different styles. So it's just kind of a mix of a bunch of different things that you can do with sequences. So this is example 10. And we're going to do what's called a telescoping sum. So as a little note, for all integers k such that k is at least 1, 1 over k minus 1 over k plus 1 is actually the same as the following. So what I'm going to do here is I'm going to actually use common denominators in order to figure out the next piece. So my common denominator is going to be k times k plus 1. And then what I'm going to do is I'm going to multiply the 1 here by k plus 1. And then I'm going to minus and multiply the 1 by k here. And then if I keep simplifying that, the k's on top will cancel, and I'm left with 1 over k times k plus 1. So this is just a little note that helps us with one of the next examples. But all that's going on here, again, as I mentioned, is I'm just using common denominators. So basically, I'm multiplying the first group by k plus 1 over k plus 1. And I'm multiplying the second group by k on top and bottom. So I'm using common denominators to get that expression and just to simplify it. So we're going to use this that I just did to find a single expression for the sum from k equals 1 to n of 1 over k times k plus 1, which is also the same thing as the sum from 1 to n of 1 over k minus 1 over k plus 1. So here, notice I have parentheses because this whole thing is being summed, right? Here it's fine because it's all stuck as one piece. But once I bring in that minus sign, I do need to keep it together to show that the entire thing is part of this summation. All right, so what I'm going to do next, I'm actually going to write out some of the terms. And something really interesting happens here. I'm just going to come down here. So I'm going to start with 1, and I'm going to use my parentheses to help me stay organized. So I'm going to plug in k as 1 first. So I have 1 over 1 minus 1 over 1 plus 1. And then summing, so I'm adding, and now I'm going to plug in 2. So I have 1 over 2 minus 1 over 2 plus 1. I'm going to plug in 3, 1 over 3 minus 1 over 3 plus 1. I'm going to plug in 4, so 1 over 4 minus 1 over 4 plus 1. And then I'm going to finish by just plugging in n. I'm going to move down here because I'm running out of room. Or maybe I'll just put it right here. But I'm going to plug in n, and I get 1 over n minus 1 over n plus 1. So let me simplify that a little bit. What you end up getting then is 1 over 1 is 1. And then 1 over 1 plus 1 is a half. So minus 1/2. And then for the next group, I have plus 1/2 and then minus 1/3. For the next group, I have plus 1/3 and minus 1/4. For the next group, I have plus 1/4 and minus 1/5. And then down at the end here, I have plus 1 over n minus 1 over n plus 1. Now, notice the pattern that's happening here. Or if you want, you can leave the parentheses too, if that kind of makes it easier to see. They're not really doing anything. But notice what's happening is that the second term in the previous group is canceling with the first term in the next group, right? A negative 1/2 and a positive 1/2 is going to cancel. And then the same thing happens here. A negative 1/3 cancels with a positive 1/3. A negative 1/4 cancels with a positive 1/4. And this is going to keep going all the way down the line. Hopefully you can see the pattern. This negative 1/5, although I didn't write it here, is going to cancel with the positive 1/5 that's going to come next. And then it's going to go all the way down, and it's actually going to cancel to here, right? So this one will always cancel with the one before it. So, you know, the 1 over n cancels here with the 1 over n here. So what ends up happening is that all of this actually becomes just 1 minus 1 over n plus 1. So this is what we call a telescoping sum, because think of it like an old telescope that you could like open up, right, to kind of like a spyglass that you could look out of, and then you could close it to shrink it back down and make it easier to carry. That's sort of what happens here. When we expand it, we can open up that expansion and show all the different adding and subtracting. But what ends up happening is most of your terms cancel, so that actually gets kind of crushed back down, and there's really only 2 terms here. So I think this is pretty interesting that you have some problems like this, some summations where they look like they're quite long and intricate, but actually occasionally it happens where you get this nice telescoping sum where things really cancel out well, and you actually can rewrite that summation as just a single expression. So that's our answer here. You could also do common denominators here if you wanted to, I suppose. So that would be n plus 1 over n plus 1 minus 1 over n plus 1. So you could also write this as n over n plus 1, right? Because these 2 1s would cancel out. So that's also correct here. But the big idea is that we're getting down to a nice single expression. So occasionally, not always, but that does happen too. All right, so we've done a lot with summations. I do want to move on to product notation now. It works very, very similar to the summation notation, except for it's from multiplication instead. So we're going to call this product notation. We're going to let m and n be integers, and we're going to let m be less than or equal to n. So the notation looks like this. Oops, let's fix this. Sorry, guys. There we go. So the symbol for product is this. I'll talk about it more in 1 second. So, and we're going to go from k equals m to n. of, we'll say A sub k. And then what happens here is you're doing the same process, but instead of adding, you're multiplying them. So you'd have A sub m times A sub m plus 1 times A sub m plus 2, again, dot, 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 all the way to A sub n here, your highest value. So a couple things. Again, the big one is this notation here. So this symbol here is actually a Greek capital P. And that's the notation here. Sometimes I do make it a little bit squigglier on top, kind of like the pi symbol. That's kind of, you can kind of see where it comes from. That symbol means P in Greek. So the capital one looks like this. I know my tops tend to be a little bit long. Sometimes they're a little bit shorter, but that's the basic idea, is that this is a capital P. P for product, right? Because you're multiplying here. So this stands for product, which means to multiply. But otherwise, very, very similar to what we've done for summation notation. We do also have a recursive definition here, where you can break off. Again, typically it's the last term, but it could also be the first term, but it's about breaking off like a finite number of terms typically. And in this case, m is any integer, and n is at least m. So the product going from k equals m to m alone is just a sub m. So just a reminder that, you know, if you have m to m of something, it's just a single term. So in this case, it's the first term, for instance, but any single term, like you can write this way. And if we want to, I'm going to write it down here so I have more room, kind of practice with breaking off a term. We could write it like this. So k goes from m to n minus 1 of a sub k, and that gets multiplied by a sub n. I like to put parentheses here around the product notation sometimes just to make it clearer. But again, if you have a symbol in between and then these are not in parentheses, then you should consider this to be a separate term. So in this case, we are breaking off the last term. Okay. And again, you could write it here without the parentheses, which again, you're assuming that the multiplication is separate. But if it's not clear, again, I tend to like to put parentheses just to really show that the different parts. All right, so let's look at a couple more examples. This is 5.1.11. And we're just going to practice some basic computations. All right, so we're going to do the product from k is 1 through 5 of just k. So what this is going to look like, start at 1. So it's 1. And again, you're not squaring it, not doing anything with it. You're just listing the value. Product means to multiply. So times, k is 2, k is 3, k is 4, all the way up to k is 5, which is the value 120 if you use your calculator. Let's do another example. So here we're going to do k over k plus 1. We're going to practice with an individual value here, right? So just going for one unit from 1 to 1. So just plugging in 1. And you'd have 1 over 1 plus 1, which is 1/2. I think I'm going to go to the next page for a second. I'm going to give you a theorem now. So mix it up a little bit here. This is theorem 5.1.1 in your text. So the first big theorem in this section. So it says this following. Let's say you have the sum for k equals m to n of a sub k plus the sum of k equals m to n of b sub k. So I want you to notice that in both cases, the sums are the same. So you have the same upper and lower bounds in each case. And that's really important. So the summation is the same. Now we're using different letters here because you would assume that those are different formulas. But if your summation part is the same, then what you could do is you could rewrite this, keeping the same summation part as A sub k plus B sub k. And you can go back and forth. So you could keep it together or you could break it back apart. So these would give you the same results. Another helpful one is, let's say you're taking a constant and you're multiplying it by a summation. You could also multiply that constant inside the summation instead. Okay. So you can bring that C underneath and bring it along with the summation. Or another way, again, if you want to just make it a little bit clearer in your own notes, you could write it like this just to show that that C is part of the summation now. Also, as a little side note here, they'll call this a single summation. So if you have homework questions that say, hey, write this as a single summation, that's what they mean. I mean, put it all back together. And then I have a product one as well, very similar to the first one. Okay, so let's say we're multiplying two products together. So we have two product notations that are being multiplied. And again, notice here the big thing is that you have the same upper and lower bounds. Then what you could do is you could put it back together. So the bounds are all going to stay the same. And then you end up doing A sub k times B sub k. So we would call this as a single product. It does help to be able to go back and forth. Sometimes one form is easier than the other. So again, it is nice to be able to go back and forth between the two forms. Okay, so let's look at an example here. This is example 5.1.12. So we're going to let A sub k equal k plus 1 and B sub k equal k minus 1. And this is going to be for every integer k. And we're going to write these as a single summation or product, depending on the notation. So for A, we're going from k equals m to n of A sub k, and then we're going to do plus 2 times k equals m to n of B sub k. All right, so there's a few different things going on here. So one thing there's a couple things you can do to start, but one thing I'm noticing here is I do see this 2 on the outside, and I do know from the previous theorem that I actually can bring that 2 inside. So that could be one way to start, is by just kind of quickly rewriting that. Okay. And then what I can also do is I do actually have formulas for A sub k and B sub k. So I definitely want to plug those back in instead. So this becomes the sum of n of k equals m. Now A sub k is turning into k plus 1. And then B sub k is turning into k minus 1. Now, the other thing from the previous theorem says that because our sums are going from the same bounds, from m to n, we can actually put this together. So this can become one big summation. So my first group is k plus 1. I'm going to add it to 2 times k minus 1, the second group. And again, I'm going to use a bracket here just to make it very clear that this is all one summation. And then I'm going to go ahead and I'm going to clean this up. So I have k plus 1. I'm going to distribute that 2. So 2k minus 2. And then I do have k, and 2k becomes 3k, plus 1 and minus 2 becomes minus 1. So we can go ahead and we can clean up that summation. If you don't like the brackets, you could also switch back to parentheses. Either one is fine. So that's how we could write that example. All right, let's do one with a product now. So the product is going to go also from m to n of a sub k. And we're going to multiply that by the product, again, from m to n of b sub k. Now, remember, again, you have to check to make sure your bounds are the same, which is important. So if your bounds are different, then you can't move things apart and put them back together. But our bounds are the same, so we can change this into one multiplication problem instead. I guess I don't need parentheses really there anymore. But it would be, you know, a sub k times b sub k as, you know, within the product piece. Let's clean it up a little bit. I don't really need those outside parentheses. Let's get rid of them. So this should be an m there. Now, a sub k we already saw was k plus 1. And then b sub k was k minus 1. And again, this is all within the product piece. So I'm going to go ahead and multiply this out. So I'm literally just going to do some foiling here. So I would have k squared minus k plus k minus 1, which gives me a final product of k squared minus 1. So that would be our final answer. So we took two more complicated products. Because they were the same bounds, we were able to put them back together to have a simpler expression here. So again, it is nice to be able to go in both directions. Sometimes it's easier to put them back together and then just have one product or summation to work with. Other times it may be easier to separate them, particularly if they're very common summations or products that you used before. If you already know a lot about them individually, it may be easier to work with the two individual ones. So it is good to be able to go back and forth between the two. All right, the next topic we're going to look at, so again, more examples here, is going to be about making a change of variable. So this question says to transform the following summation by making a specified change of variable. All right, so the summation is going to be from k equals 0 to 6 of 1 over k plus 1. And our change of variable is going to be j equals k plus 1. It is pretty common to switch our variables around. Now, one thing I will note, if you're not planning to change the format of anything, to change the bounds or change the format, you could just use whatever variable you wanted to. So like if I want to make this an I could just change this to I is 0 and I plus 1. That's fine. Or I can make this, I don't know, J is pretty common, K, M, whatever you want. So if you're not changing the bounds or the formula, you can change variables as much as you want to. The difference here is that we're not just replacing J with K, we're replacing J in place of K plus 1. So what that ends up doing is it changes the look of the formula and it actually shifts the bounds. So you end up with the same sequence or same summation here, but it's going to look different. So it's going to be one of those examples where you end up with the same outcome, but it looks like a different sequence or a different formula to start with. Here, summation. So again, you don't want to think too hard here. So the first thing we're going to do is calculate the new upper and lower bounds. So our original bounds were k equals 0 and k equals 6, right? So that's what my original ones were. My new formula is j is equal to k plus 1. So what happens here is, well, if k is 0, if I plug that into my formula, then j would be 0 plus 1 equals 1. And then here, again, if I plug in k is 6, I get 6 plus 1 is 7. So my lower bound was originally k is 0. It's now going to be j is equal to 1. And my upper bound was originally k is 6, and it's now going to be j is equal to 7. That's pretty obvious here, right? Because you're just adding 1 to each of them. So you can see that the 0 goes to 1, the 6 goes to 7. And then the other thing you're going to do is you're going to fix the formula, basically. So we can say calculate the general term. So it's often called the general term, or you can just think of it as like the formula or expression that's being used. So we have j equals k plus 1. So what we can do is solve for k. And you can do that by subtracting 1 to both sides. So just some basic algebra. So k is also the same thing as j minus 1. And then what you can do is you can take the original piece of the formula, replace the k with your j minus 1, and you can get the new formula is going to be the ones here will cancel, is just 1 over j. So our new summation is going to be from j equals 1 to 7 of 1 over j. Now, if you were to check this, and that's a great idea, is you should get the same exact summation as the original. So we're not actually changing any answers here or any values or anything. We're just using a different expression, basically, for the same outcome. So very similar idea to how multiple different formulas can work to produce the same sequence, for instance. So we call this a change of variable. And again, it's not just like replacing the variable and making them equal, but usually there's some sort of shift to it. So here we're adding a 1 in. So those bounds are going to shift, and then the formula will also shift. But if you were to plug in the values, you would get the same exact summation. As a little side note here, because I've been mentioning this, so let me go back to my original here of k. If I wanted to, so we just saw that this becomes this, which is the same thing as j going from 1 to 7 of 1 over j. Another common thing to do at the end is if you don't like j's, you can switch it to any variable you want. You actually could switch it back to k, as weird as that looks. And again, it's the same thing. So here it's, you don't have to worry so much about using k as like a variable here. It's a little bit different. So it's called instead really a dummy variable, right? Because it works very similar to a variable, but you actually can replace it and use any letter you want. It doesn't have the same meaning as it does in like proofs where it has to have one value the entire time or represent like one particular answer. So again, you may notice on some of the homework questions and things that once you make that change of variable, they may want you to actually go back to the original variable instead. So in that case, what you're doing is you're not plugging everything back in, you're just literally changing the variable. So you have your new summation, and then you can switch it to any variable that you want to. So here we can go back to that k if we want. All right, our next example, again, doing a little bit more with summations here. We're going to rewrite the summation, which is going to go from k equals 1 to n plus 1 of k over n plus k, so that the lower limit becomes 0 instead, and the upper limit becomes just n. So again, you kind of just have a shift here. We don't really want to change the answers. We just want to have different bounds to start with, but I still want the same output. So what you could do here as a start is you could make an educated guess. For the change of variable that we're going to do. Right, because we are really shifting the whole bounds here. So this is sort of like a hidden change of variable problem. So what's happening here is instead of my k being 1, I'm going to go down to 0. Instead of this being n plus 1, I'm going to go down to n. So I'm basically subtracting those two things by 1, right? So an educated guess here could be, well, let's let our new variable j be k minus 1 instead, right? Because what we want is we want something like j goes from 0 to n, right? That's really what I'm looking for. I want my new bounds to be 0 to n here. So my educated guess is that if I subtract the k by 1, that seems to shift the bounds how I want to. So let's actually check it. Let's make sure it works. So our original starting values were k equals 1, and our ending value was k equals n plus 1. We're going to try j equals k minus 1. So if I plug in my k, I get 1 minus 1, which is equal to 0. So I do get j equals 0. That works. And let's double check that the other bound works. So if I plug in n plus 1, subtract 1, those ones cancel, I do get n. So I do get that my bounds are working out. So by subtracting with 1, I'm able to get the lower bound to be 0 and the upper bound to be n. So we take an educated guess there, and you do want to just check, are the bounds actually working, right? So I'm checking, does the lower one work and does the upper one work? Then what you're going to do is you're going to change over the expression, right? So now we're going to change over the general term, or you can think of it as the expression or the formula. So the original expression was k over n plus k, right? That was the original one, what we're starting with. We are changing it to j is equal to k minus 1. So if I solve for k, I add 1 to both sides, and I get that k is equal to j plus 1. So this is what I can plug in to my expression here. So this becomes j plus 1, and then n plus j plus 1 in the denominator. There's nothing I can really do to clean that up, right? So that's as good as it's going to get. So putting this all together, j is going from 0 to n, and the expression is going to be j plus 1 over n plus j plus 1. Okay. And like I said before, if you prefer, you can switch the variable if you prefer. So this is not a true change of variable. This is just that dummy variable switch. So if you don't like the j here, you could go back to the k, but you're not actually switching anything else around. You're leaving the formula as it is, and you're just changing the variable. Or if you don't like j, I don't know, use t, use n, use, oh, not n here, but use, I don't know, s, use something different, right? So you can change those variables over as often as you like. This is different because we're actually shifting the bounds. So that's a more difficult change. Okay. The next big topic that we're going to do, and this could be a good time for a break if you do need a break. So we're still in section 5.1, but there's kind of one more big part we're going to talk about here, and that is on factorials. So we're going to review factorials and also the n choose r notation. Now, if you've already had statistics or some other maybe higher level math classes, this may be review for you. And that's okay too. So if not, then we're going to go through it here and you'll learn it here. but this is stuff that is actually pretty common in other math classes as well. So if you've seen it, then just kind of take some notes and you can get a nice review. So n factorial, when we say n factorial, the symbol we use there is n with a exclamation sign. That is a symbol for a factorial. And it basically just means to multiply downward. So for instance, you would do the n times n minus 1, n minus 2, n minus 3, all the way until you get down to 2 times 1. So let me give you a concrete example so that it makes sense. 5 factorial would be 5 times 4 times 3 times 2 times 1. And then you can just do that out on your calculator and get 120. Let me get my calculator out here for a second. So there's a couple of different places that you can see factorials, by the way. So I have, let me get here, the graphing, it's called Graph and Calc 83 or Graph and Calc 84 app. It looks just like an 83, 84 calculator. So if you have one of these, you have a factorial key under Math. So if you go to Math, and then you go over here to PRB for probability, you can see your factorial key right there at number 4. So for instance, I could do 5 and then go to Math and go over to that factorial key and then hit enter, and I could get the 120. If I don't have a factorial key, then you could just multiply 5 times 4 times 3 times 2 times 1 and do it manually, and that's fine. I have an iPhone in particular. So if you have an iPhone, in case you don't know yet, if you turn your iPhone to the side, a much larger keyboard will open. And you do have a factorial key on here. It's actually right here, that exclamation point. So you could hit 5 factorial and then do your factorials here. So try it out on your calculator. Make sure you know, try the answers, like try 5 factorial, make sure you know how to get the right answer, but see where your factorial key is on your calculator. And that will make your life a little bit easier. As a side note here, definition, 0 factorial is automatically 1. 1 factorial is also 1. So for those, you can think of that more as just a definition, but 0 factorial and 1 factorial are both 1. There is a recursive definition here. So n factorial is 1 if n is equal to 0, or it's n times n minus 1 factorial if n is at least 1. So what you're doing here is, again, you're taking that last term off. This is actually really helpful in a lot of formulas with factorials. By taking that highest power off, that highest factor, it actually makes a lot of proofs and things easier. So just as an example, just to see what this looks like. For instance, like 5 factorial, you could write as 5 times 4 factorial. It's the same thing, right? 4 times 3 times 2 times 1. Or, 9 factorial is 9 times 8 factorial. That's what this formula is looking at. It seems silly, but it's actually really helpful in a lot of kind of random cases. So it is worth noting there. All right, so let's do some examples. This is 5.1.16 in your text. So example 16. And we're just going to simplify. So I'm going to show you a couple of ways so you can do this. So I'm going to do 8 factorial over 7 factorial. Now, the first way you could do it is to just use your calculator, right? So if I wanted to, I could type in 8 factorial, hit enter, and I get 40,320. And then I could do 7 factorial and I get 5,040. And then I could just divide those values. 40,320. And I get 8 for the answer. So that is one way to do it. You could do it in your calculator. So if your calculator is pretty decent, you could do 8 factorial divided by 7 factorial. Just make sure on the iPhone, like you hit the enter key again. Some of them are a little bit different how they work. So you could do the whole thing in your calculator. One thing you do not want to do, though, is don't do 8 divided by 7 and then try to do the factorial like that. That does not work. So you do have to do them individually. The other way to do it is to just think of it more manually. So for instance, 8 factorial over 7 factorial is the same thing as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 7 factorial is 7 times 6, 5, 4, 3, 2, 1. And what happens here is everything cancels in pairs pretty nicely with factorials. And for this particular case, you only have the 8 left. So that's really why the 8 is left over. You do get nice answers when you're dividing with factorials because a lot of the pairs all match up. And one last way you could do this as well is you could use that recursion formula I just gave you and recognize that 8 factorial is the same thing as 8 times 7 factorial. And it just saves you a lot of writing, and those 7 factorials will cancel. So there's a couple different ways that you can work this first problem. All right, here's another example. And again, there's more than one way to do this. I like to try to cancel most often by using this recursion formula. Now you can not just take out the first term though, you could take out a couple. So for instance, watch this. So 5 factorial is the same thing as 5 times 4 times 3 factorial. So what I'm doing here is I'm taking off the last 2 terms and then I'm stopping at the 3 factorial. The reason I'm doing that is because in the denominator, I have a nice 3 factorial that I can cancel right away with. And then I'm left with just 5 times 4, and then 2 factorials, 2 times 1. So 20 over 2 is 10. Again, this is just one way to do it, but it's a really nice, helpful way. Let's do another one here. 1 over 2 factorial times 4 factorial. So here, how you can add with factorials. This is actually kind of an interesting idea here. So one thing to note, again, I'm going to use that recursion definition, is that 4 factorial is just 4 times 3 factorial, right? And then over here, what happens is 3 factorial as well is 3 times 2 factorial. So we can kind of use this to help us find a common denominator here. It is a little tricky to kind of get used to it. But if I just rewrite this, in the first group, I have a 2 factorial, I have a 3 factorial, and I have a 4. In the second group, I have a 2 factorial, a 3 factorial, and an extra factor of 3 here, right? So if I break these down a little bit, so I can notice right away that each of these pieces, right, has a 2 factorial. Each of these pieces has a 3 factorial. 3 factorial. And then the first group has an extra factor of 4, and the second group has an extra factor of 3. So I can use those factors of 4 and 3 as my additional multipliers to get a common denominator. So what this looks like here, let's get one more color out, I think, is the first group. Again, I'm missing that factor of 3 from the first group, so I can multiply by 3 over 3. And then for the second group, I'm missing this factor of 4, so I can multiply by 4 over 4. And what I get here then is I get 3, and then now I have the same thing in the denominator in each case. And then I get a 4 on the other side, again, with the same denominator in each case. So I'm just going to make this a one big denominator here, save us a little bit of writing. So let's think about what we have here. It is a little tricky to kind of look at, but I think the first one is maybe the easiest to see. So you have a 2 factorial, a 4 factorial, and an extra factor of 3. Well, what I could do is I could put the 3 and the 2 factorial back together here. And then I would have a 4 factorial left, but the 3 times 2 factorial is the same thing as 3 factorial. So I'm able to simplify that denominator into 4 factorial times 3 factorial. You actually can see it here as well. So for instance, right here, if I have a 3 factorial times a 4, I can put those back together as 4 factorial. So I'm using that recursion answer backwards. Instead of taking them apart, I'm putting them back together. So it's pretty common for us to kind of take parts of these factorials on and off as we see fit to make the problem easier. I'm not changing the problem. I'm still using all my math rules, but I'm, again, just making it a little bit easier to handle. Now, 3 plus 4 is 7, and if you actually do on your calculator 4 factorial times 3 factorial, you do get 144. So a way that we can add those fractions. Let me just pause for a second because I think this is the trickiest one of all. So what we're doing here again is we're trying to get a common denominator because we're adding fractions. So you need the same denominator. And I'm going to do it with the factorials. What I'm noticing in the first group is that 4 factorial I can break down as 4 times 3 factorial. And then the second group, that 3 factorial, I can break down, or one of them, as 3 times 2 factorial. So I'm able to recognize that 2 of the 3 pieces in the denominators are the same. So that's why I'm using the 3 and the 4 as my multipliers to get the common denominator. The next piece that's a little bit tricky is to put the factorials back together. So it always works with a factorial and then 1 unit higher. So here you have 2 factorial and then you have times 3. That's 1 unit higher. Then it makes a 3 factorial. Or here I have a 3 factorial times 4. So I can put it back together and make it 4 factorial. It is the same exact thing, because 3 factorial is 3 times 2 times 1, and then you're timesing by 4. So that's the same thing. You're getting all of those multiplication factors right down the line there. So it does take some practice to kind of get used to it. But we can pull those factorials apart and put them back together as long as we're careful about it. One last example here too, using an n. So if I start with n plus 1 factorial over n factorial, again, I'm going to use that recursion definition. So what I can do is notice that, well, n plus 1 factorial would be n plus 1 times n minus 1 all the way down to 2 times 1, right? So I'm going to take that first term off, which is n plus 1, and then I'm going to leave the rest as a factorial. And that's going to be n factorial. And then that allows me to cancel with the n factorial in the bottom. So this expression actually becomes a lot simpler than we think. So again, this is a really common idea. If I have 6 factorial, I can write this as 6 times 5 factorial, or I could keep going 6 times 5 and then leave it as 4 factorial, or 6 times 5 times 4 times 3 factorial, etc. I could keep, again, pulling a term off each time until I get to a factorial that's helpful for me. And helpful usually means something that we can cancel with. Okay, so something like, again, just kind of another quick example here, 7 factorial over 4 factorial. Well, I could write 7 as 7 times 6 times 5, and then I'm going to stop at the 4 and leave that as a factorial because it's going to cancel with the denominator. So again, we really just kind of pull off those terms as we need to, and then it just makes the rest a little bit easier. Now I can multiply 7 times 6 times 5 to 210. All right, one more example here, n factorial over n minus 3 factorial. So this is going to be similar to this one actually, where I can pull off, again, those ending terms for the factorials. So the first one is n. The next one will be n minus 1, just going down the line, then n minus 2. Then it's n minus 3, and I'm going to stop and write the rest as factorial because I see I have an n minus 3 factorial in the denominator. So I, again, take off as many leading or ending terms as you need to in order to get something, it just makes the problem a lot easier to work with. So that's some work with the factorials. Now, the next formula I'm going to give you guys here is the n choose r formula. We often write it as NCR, by the way, if you've seen that before. This appears often in stats classes or on calculator notation if you have it there as well. So sometimes you can see these on calculators or Excel, etc. So a lot of tech could do this. We can also write it like this, n choose r. And the formula is n factorial over r factorial over n minus r factorial. A couple of things here. N and r have to be integers, and r has to be basically less than or equal to n, and they're both positive, or 0 or bigger, I should say. But r has to be at least no bigger than n, right? Because you can't, if you have 5 objects, I can't choose more than 5 of them. So that's really what it's about here. So let's give it a concrete example. So let's compute 8, choose 5. So our n here is 8, and our r is 5. So what we're saying here is the following. So we are choosing 5, let's say, items out of 8 options. And in this case here, when we say and choose R, order doesn't matter here. Which means, like, let's say I number my objects 1 through 8. So if I chose, 1, 2, 3, 4, 5, it's the same thing as choosing 1, 3, 2, 4, 5, right? So they're the same 5 objects. So that's what we're saying here. There's no difference in order where, like, there's no first place, second place, third place. Order doesn't matter. So, objects 1 through 5 are the same, whether I arrange them in order or if I put them in, backwards order or something like that, it doesn't matter. So questions like this mean basically, let's say you have 8 items and you want to randomly choose 5 of them. And sort of the question that comes out of this is, how many different ways can we do this? That's really the question here, is how many different ways can we do this? So you're going to use the formula. So you just plug in, our n is 8, so it's going to be 8 factorial. Our r is 5, so 5 factorial. And then I would do 8 minus 5 factorial. Clean this up, 8 factorial, 5 factorial, 8 minus 5 is 3. Again, if you want to use your calculator here, you're more than welcome to. Just be really careful typing things in that you're not mixing things up, so take your time. 8 factorial is on top. In the bottom, you're multiplying 5 factorial times 3 factorial, and then you're doing the full division. I like to do it more by hand. So I'm going to write the 8 factorial as 8 times 7 times 6. And then I'm going to stop at the 5 because I notice a 5 factorial in the bottom that I can cancel with right away. And then in my calculator, I'm just going to do 8 times 7 times 6. And then in the bottom, I have a 3 factorial left. And if you do this out in your calculator, it's a little bit easier. You get 56 as your final answer. Again, it doesn't really matter too much to me how you do your work here, as long as you can figure it out. But do be careful. Your answer is 56 here. So if you're using more of the calculator work, just make sure that you know how to type it in so you're getting the right answer. So definitely practice before you go to the homework, again, just to make sure you know how to do it. If your calculator has a N choose R feature on it, you could use that too. So the TI 8384s do have that feature. So again, you could use that if you like to. So another example. 4, choose 4. So our n is 4 and our r is 4. So use the formula. N is on top, so 4 factorial, then r factorial, and then n minus r, which is 4 minus 4 factorial again. So I have 4 factorial on the top, a 4 on the bottom. 4 minus 4 is 0. Now what happens here is these two do actually cancel out. Don't forget 0 factorial is 1. Now there is always a 1 on top, right? Because technically, a number divided by itself is still 1. So it doesn't just completely go away. This answer does end up being 1. And that's going to happen if you have 4 objects and you have to choose all 4 of them. There's only one way that you can do that. Now you can also do this with kind of leaving variables or placeholders in there. So compute n plus 1, choose n. So for any n, right, we're not specifying what the n has to be, right? If n was 5, this would be compute 6, choose 5. Or if n was 7, we'd be doing 8, choose 7. But I don't know that I have the n there. So I'm going to use my formula, but I'm going to leave it as the variable notation. So for n, I'm going to plug in n plus 1 instead. So this becomes n plus 1 factorial. For r, I'm going to plug in n instead, n factorial. Then I'm going to subtract the 2, so n plus 1 minus n, and that is another factorial. Let me just clean it up for a second here. Here the n's are going to cancel, and I have a 1, I guess I don't need parentheses there anymore, but a 1 factorial. Now, 1 factorial is just 1, right? So just like 0 factorial is 1, 1 factorial is also 1. So it's not really going to make a difference here. But what you could do is you could pull out that last factor of n plus 1, and then write the rest as n factorial. Again, that 1 isn't going to make a difference. It's just going to clear out. And you actually are able to get down to the answer of n plus 1. So no matter what n is, I could actually figure out how many different ways there are to choose n objects if I have n plus 1 objects. So we could also use that formula with variables. All right, so last thing, I'm just going to very quickly kind of tie this into some more application. So an interesting thing I think as one example for a factorial that I usually teach in stats, for instance, is let's say you have a 4-digit PIN. With no repeats. So for instance, you have to choose a 4-digit PIN. Now your digits are typically 0 through 9, right? So for instance, you could choose your PIN 7, 8, 1, 2, for instance. But what happens here is you have 10 digits. So if you do 0 through 9, you actually have 10 digits that you can choose from. And you get this idea of, well, if I have 10 digits, in the first case, I have 10 options I can choose from. Then there's 9. Then there are 8. And then there are 7, right? So you do have this kind of factorial-like idea here, often with passcodes and pins, particularly if you're not allowing repeats. If you do allow repeats, then again, you have more options. It would just be 10 times 10 times 10 times 10, because you could repeat the same value, right? Your pin could be 1, 1, 1, 1 if you wanted to. But there are some nice applications really with factorials in particular here. Okay. We can't quite do this one using the combinations we just did, like so choosing, so and choose R, because order actually does matter here. So right, the order of the pin 7812 is not the same pin as 7128. So actually there's a different formula for that called a permutation, which is very, very similar. It also uses factorials. So we're not going to worry about that today, but do know that there are lots of applications with factorials here. And I know in my stats class, I have a fun time kind of doing a lot of password stuff with them. So it is very factorial-like if you're not allowing repeats in particular. And then also, like I said, here the formula we're using is n choose R, where order does not matter. So not quite the same for passcodes, but we do have similar formulas for called permutations that do work, that do allow order to be important there. So there are, again, some applications here as well. One last application that I do want to just briefly talk about is sequencing in programming. So one-dimensional arrays in computer programming basically consist of finite sequences. So for instance, I'm going to give you the following segment here. So let me give you 2 segments for a second. You can copy these down at home. K equals 1 to n. Sorry, guys. All right, let me pause for a second. My dog is going to say hi to you guys. He's very needy. All right, let's try that again. So again, just a really quick, another application. So one-dimensional arrays in computer programming can relate to sequences as well. So here you just kind of have, two, I don't know, mini programs, right? Or mini segments of program, something like that here. And they actually both give the same output. So they both give the same output, which is the sequence from k equals 1 to n of a sub k. And then what's happening here is we are using brackets for subscripts instead. So in this particular, I don't know, our pretend programming language, we're going to use the brackets for the subscripts to show the difference in sequences. So again, it just kind of reiterates the idea as well that different programs, just like different formulas for sequences, can give you the same output. So that ties in here as well. So here you can see you're starting with a sub 1, and then for k equals 2 through n, you're taking the original s, which is a sub 1, and then you're adding it to the next a sub k for the next k. So going from 2 all the way through n. So you're getting that sequence from a sub 1 all the way through a sub n here. In this case, again, just slightly different setup. Here you're starting with 0 for your S. And then here you're working from k is 1 to n. So your S becomes the original S plus the next k. Now the original S is just 0, so it's not coming into play really here. And then your A sub k's are going from 1 to n. So in both cases, you have a basic sequence of 1 to n for A sub k here. Again, like I said, the notation in our text, are we using the brackets instead of subscripts to represent that sequence in this case. And there's lots of applications. So one application, if you want to, kind of read more about it, is converting base 10 to base 2. By repeated division. So again, if you're interested, you can kind of read more about that, but just kind of that little bit of tie-in as well to computer programming and how sequences can relate to computer programs, and also the idea that, many sequences and many programs can be written in different ways and have that same output.